Hello there. Today I'm going to continue my discussions on counting distributions. Please be patient with me. What did we do last time? Last time we counted the number of distributions of n distinct objects into k identical objects and the number was the result or the number was or is the sum of the Stirling numbers nk where k varies is nj where j varies from 1 to k. Okay, that gave us the number of different ways of distributing n distinct items into k identical boxes, identical containers. Today, we are going to count the number of ways to distribute n distinct items into k distinct boxes. That's the difference, okay? So, what I am interested, of course, it's very easy to see that there are k to the power of n such distributions, okay? I'll discuss it next time. But now, we are going to make use of the tools we have at hand to determine a formula to count such distributions. Okay? Now let's go back to yesterday's and begin by counting. Okay, so we know, or we have seen that there are S and J ways to distribute n distinct objects into j identical boxes where no box is empty after a distribution, right? Now, what happens if those k or if those j boxes are the same? Now let's consider what if these j boxes are distinct? Well, the fact that they are distinct tells us that this kind of arrangement is different from that one. Okay? Order matters. Now, order has to be, introduced in such distributions because one distribution with this order is different from the same distribution in that order. Okay? So, that would lead us, that the number of permutations or different arrangements of k distinct objects is k factorial. Therefore, now boxes are distinct implies that order is important. Order is important. Therefore, and we know that there are j factorial permutations of j distinct items. Okay, in that case, the result will be modified too. So if the boxes are displayed, then there would be S and J times J factorial distributions. You see? The fact that the boxes are distinct has turned this into this, or we multiply it by J factorial, because for each of these distributions there are J factorial corresponding distributions when order comes into play. So now we are ready to solve the problem. Today's problem, that's the case where, we don't care about which box remains empty or not. So solving today's problem, so we have seen that for each J, we have J factorial times S and J. And we remember we had a sum to solve our last time's problem. So what we are going to do is, let's assume that. Now consider a distribution of n distinct items into k distinct boxes. Okay? Boxes are distinct. Now suppose exactly J boxes are non-empty. This will allow us to use Stirling numbers of second kind. So this means there are, for each J, there are, we have K boxes. It is out of the K boxes that we pick J of them and then permute them. So there are Kj times S and J. You see, for each J, we do have such number of distributions into J boxes where J, none of the J boxes is empty. Okay? Distributions. Therefore, adding this for J varying from 1 to K, we have that is P Kj times S and J, where J varies, J goes from 1 to K, counting what we are interested in, the number of ways. Because at the time we have exactly J boxes, which are non-empty. Exactly. So, you see, we have that number counting the number of ways and distinct objects can be distributed into K distinct boxes. Okay? So let's see an example. Actually, you can check that this is exactly equal to K to the power of N. We are going to see an example to verify that. Now I have Stirling a table here. You can see it there. Just some values of the Stirling numbers, okay, of the second kind. So I'm going to take the fifth, let's say the sixth row, okay. I'm going to count the number of ways 6 distinct items are distributed into 4 distinct containers. So we'll see what happens. So let's see an example. Take the case n equals to 6 and k equals to 4. I'm going to write these numbers here, there. SN1, 131, 90, 65, 1, 31, and 65 are the numbers we are interested in. This one is S61, this one is S62, and here we have S63, and here we have S64. These are the numbers, the Stirling numbers of the second kind that interest us. Okay, so the number of ways to distribute. Build 6 distinct items into 4 distinct boxes is nothing but equal to the sum j varying from 1 to 4 of S6j times P4j times P4j. Well, this means this is equal to S61 times P41 plus S62 times P42 plus S63 plus P43 plus S64 times P4. Okay? What are these numbers? Well, S62 is 31. We have 31 there. S63 is 90. 64 is 65. So we are going to have P41 is 4 factorial over 3 factorial, which is 4. So this is equal to S61 is just 1. So 1 times 4 plus, here S62 is 31. P42 is 4 factorial over 2 factorial, which is 12. Okay, so it's 12 times S62, which is 31 plus, and here we have S63, which is 90. P43 is 4 factorial, so it is 24 times 90 plus S64 is 65 times 24. So this is 24 times 65. Okay? And let me do some that and that and that. 40, Okay. I know this number is 4096. Now look, 4096, as I have told you earlier, this number would add up to 3 minus 4 to the power of 6. Let's check. 4 to the power of 6 is simply 2 to the power of 12. You know that 2 to the power of 10 is 1024 times 2 squared, which is 4. 4 times 7 is 48. 96. Okay? So, thank you for having followed the lesson, and see you next time.